It's really an honor to be here. I'm really excited about this conference, learning a lot. So in my talk, I'm going to be talking about quantum systems open to the world. And in particular, I'm going to merge two of the topics of this session, which is light and atoms. So it is conventional wisdom that quantum systems must be isolated from the environment to preserve their properties, for the properties to survive. And this is a problem because in quantum mechanics, the environment is always there, even if there is vacuum, because there is always some form of vacuum fluctuation. So I am interested in how open quantum systems formed by many particles are able to display order or some other interesting behaviors, such as coherence, not despite being coupled to an environment, but precisely because they are coupled to an environment. So instead of isolating this system and engineering the properties of its evolution, my work is about how to use dissipation and openness as a resource to build structures that are somewhat ordered in space and in time in an emergent fashion. So maybe making an analogy with a very classical object and aiming for a high goal, the question would be, can cathedrals build themselves without architects? What is needed for that? In what type of environment could that happen? So let's go one step at a time. So I want to begin by discussing an example that may be familiar to everyone. So imagine that we have some dye, and we put some drop of this dye in water. And so dye is now our system, and water is our environment. And we know that as time progresses, diffusion is going to occur. And eventually, we're going to end up in some sort of boring state where we have lost all structure, and now we have some just uniformly colored liquid. This is a process of where disorder grows and entropy is being produced. It's also a process that is irreversible because it can only go in one direction, which is basically a signature of the arrow of time. And so it proves that basically in many situations, or even maybe most situations, order is not guaranteed. On the other hand, we know in quantum mechanics or in physics, that there are order phases of matter that occur in systems that are at thermal equilibrium. And by thermal equilibrium, I mean situations where the average properties of the system do not change in time. Such systems are well described by statistical mechanics, which is a theory in physics that we've known for a while, and it is well established. So illustrated in this slide is the emergence of magnetic order. Magnetism is actually a quantum phenomenon, which happens at room temperature because basically critical temperature for magnetism to be destroyed is just too high for us to observe in our daily life. So a ferromagnet is basically described as a collection of little spins, which are these little arrows. And at high temperature, basically fluctuations break long-range order, and you end up in a system that is not magnetized. On the other hand, as we decrease the temperature, these spins want to align, and eventually at low temperatures, this cooperative behavior of the spins dominates over thermal fluctuations. So this is really a process that is cooperative, which means that the macroscopic behavior of such a system is very different from that of a single spin. There are more sophisticated phases of matter that are also possible. So in this slide, for instance, are examples of superconductivity and superfluidity. And these phases of matter are perhaps more sophisticated because now what happens is that there is macroscopic quantum coherence emerging in these systems. So basically now you can describe these particles as sharing some macroscopic wave function, or there is some phase relation between these particles. And actually, this type of systems were very beautifully described by the talk of Francesca. But the important thing is that these are equilibrium phases of matter. They are stable, and they emerge below a certain temperature. Okay, so now if we think about the the world that we see with our eyes daily, this idea of order emerging as we lower the temperature is really in contrast with our human experience. And this is because there are many examples where order or structure emerges not because of low temperature, but because of connection to an environment, because of energy pumping, because of dissipation, because of fluctuations, because of noise. And this typically happens because these systems are out of equilibrium and they are exchanging continuously energy and information with an environment. So this paradigm is not captured by equilibrium statistical mechanics, in many of the cases, this order is transient. So let me just show you like this, or discuss this couple of examples. So the first case is a chemical reaction with a very complicated Russian name I cannot pronounce, but as you can see, there is a very striking spatial structure that contrasts very much with the boring kind of diffusive uniform behavior that I discussed in the beginning. Another example of transient order in open systems is actually our life. So eventually entropy will win, actually will die, but for our life we are structured and ordered creatures. Zooming out, we have cities, and zooming even more out, we have our own planet, where, for instance, this morning there were beautiful discussions about how this is a very nonlinear, out of equilibrium system. So, the bottom line is that there are many systems where dissipation and fluctuations are sources of order. And typically, this requires many particles that are interacting, and physics has a hard time dealing with them. So, as a last connection with, maybe not quantum problems, I want to discuss that, this order does not need to be just spatial. It can be temporal. So this is an example of a spontaneous emergence of synchronization in fireflies. So then the question is, can we have such a behavior, in particular desynchronizing behavior in quantum systems? What would that entail? And so we need for particles to see each other, and we need to have many particles, and we need a system that is out of equilibrium. This seems to be the common ingredients. When we have a quantum system consisting of many particles, as I said before, the environment is always there. And even if that environment is in vacuum, basically there will always be fluctuations that cannot be switched off, which means that actually these fluctuations can be used as an ingredient to promote self-organization. Okay, so now let me narrow down a bit in the type of systems that I'm interested in. So in the last few years, as Emmanuel actually showed very, very beautifully with amazing pictures, people have become really proficient in generating ordered arrays of atoms in free space, which are trapped in optical lattices or optical tweezers. So in these pictures, you can see every point is an atom fluorescing, and the light is being captured by a camera. And so these structures can be generated in 1D, can be generated in 2D, and then if you are friends, you may want to generate them in 3D, and you can build an Eiffel Tower, which is what is displayed there. So the typical distances between these atoms ranges from hundreds of nanometers to microns, which means if you now shine light into them, they are going to, these atoms are going to interact with light collectively, and in particular, they will be resonant, they will interact with light that is optical light, so also of hundreds of nanometers, which is comparable to the distance between the particles. So these examples in the top row consist of atoms in 3D vacuum, 3D free space, but there has been also efforts in controlling the environment, so basically engineering the environment by placing atoms close to dielectrics. So I'm showing an example of atoms being placed close to a photonic crystal that has a band gap and modifies how light propagates in the structure, and therefore how atoms talk to each other. And the last comment is following with what Bill said, is that this physics goes beyond atoms and photons. This is a system that consists in superconducting qubits. These are transmons, which are elements that, for instance, Google or IBM used to build their prototypes of quantum computers, and they are connected via transmission lines, which is a one-dimensional reservoir or bath, and they basically talk to each other, not at optical frequencies anymore, but at microwaves. Okay, so let's see what type of emergent behavior can happen in these systems. And so we're going to start discussing that by just looking at a single atom as an open out-of-equilibrium system. So basically, as Francesca said, atoms are extremely complicated creatures, but I'm a theorist, so for me are two-level systems, okay? They consist of a ground state and an excited state separated by an energy gap, which is proportional to the frequency of the light that would be emitted if the atom goes from the excited to the ground state. If I, by means of a laser, for instance, I place the atom in the excited state, I know that after some time, the atom will relax to the ground state by spontaneously emitting a photon. And this is a stochastic process driven by quantum fluctuations of the electromagnetic field. So let's try to do some thought process. I'm going to put the atom in the excited state, and I'm going to track, for how long the atom is in the excited state. So the atom will be in the excited state for some time, and eventually it will decay emitting a photon, which I will detect with a photodetector. It will go click, and then I know that the atom is in the ground state. If now I try to do this experiment again, what I will find is that this quantum jump actually happens at a different time. And this is because this is really a stochastic process. So basically, yeah, it happens at a random time, and also the photon is emitted at a random direction. And then I do it again and again and again, and then eventually I recover the typical exponential decay that one would expect with a lifetime or basically decay rate that is determined by the environment. So depending on the environment my atoms are in, this lifetime can be decreased or enhanced. Okay, so now let's think about what happens when we have actually many atoms talking to each other. So what happens actually that they will superradiate. And this is an example of emergence of coherence by dissipation. So I'm going to explain to you a little bit what that means exactly. I'm going to first talk about the panel in the left, where I'm going to consider that I have a bunch of independent, as in non-interacting atoms. I have a photon detector, and I count photon counts, and this is what happens, what is represented in the top of this figure, and you'll see a bunch of clicks. And these clicks are basically happening again at a random time, because the atoms, if they are non-interacting, they don't know that they have anybody around. So basically what happens is that if you look at the photon emission rate versus time, what you get is actually a quite boring, again, exponential decay. Now, this calculation, I should say, is very easy to do because the atoms are non-interacting. On the other hand, if I now start to consider that atoms are interacting, the calculations become really, really hard, as Emmanuel discussed in his talk. So one could imagine that the problem of light interacting with matter has been solved because it's a problem that has been with us since the beginning of times. But actually, this problem at a quantum level is basically a problem of a strongly interacting quantum system that is open to an environment, and this is a hard problem. And actually, if you try to compute things exactly, you will run into the problem that Emmanuel said: your computer dies. So actually, these plots are for 16 atoms. There is no computer in the world that can do that for 20, for instance, which is kind of humbling. Okay, so now let's try to, I'm going to show you what happens when you have interacting atoms. So you have interacting atoms, and you look at the photon counts. What you see is that they all become clumped. They all happen all at the same time. If you do this experiment again, you will see that maybe these photon counts, change a little bit, but again, they will tend to be clumped. So this means that the photon emission rate will be peaked at a certain time, and this basically means also that this is a process where via dissipation, via photon emission, in this very reversible dynamics, atoms are synchronizing. And they are synchronizing because every time atoms emit a photon, they do it in some indistinguishable way. Basically, you cannot tell from what atom that photon came from, which basically imprints some phase in them. And by doing this repeatedly, this phase is reinforced in the system. And then physicists care a lot about the scalings. So a natural question is, this peak of emission, how does it scale with system size? And in particular, what determines this synchronization? Is it the distance between the particles? Is it the dimensionality of the array? Is it the environment? So actually, this is what I've been doing in the last few years, is trying to understand or derive emergent laws for this type of problems without having to solve for exact dynamics, basically because I can't. So the idea is that although this is a complicated problem, we can derive a lot of intuition by understanding the type of couplings between the atoms that I have depicted there as some sort of network. Again, in physics, we're very good at understanding limits. So the limit of this plot below is, okay, thank you, I'll be done by then. The limits are very well understood. So for instance, if you have systems that are non-interacting, which will mean you don't have any lines connecting the atoms, we know that the maximal emission rate is n times the spontaneous emission rate of a single atom, which means that per atom, there is not a growing decay rate or photon emission rate. On the other hand, we understand actually since Dickey wrote a paper in 1954 that the maximal emission rate, if all the atoms are maximally interacting, so if basically all these lines connecting them are of the same strength, the maximal emission rate is n squared. And then the question is, what happens in between? And what happens in between matters because now is no longer a dream. The possibility of creating these exciting geometries of atoms in 1D, in 2D, and 3D, and so forth, and also putting them in engineered baths. And what we have found actually is that the interaction range really matters. So if you had only nearest neighbor interaction, you would basically find particles, even though they are interacting, they behave as if they were not. The same happens if you have really a line of atoms in free space, even though they have long-range interactions mediated by the electromagnetic field. But as you increase the dimensionality of the system, this emission rate becomes larger and larger with an exponent that depends on the dimensionality. And so this speaks to the capacity of this type of systems to self-organize as the dimension increases. Okay, so then the question now is, why should we care about this? And there are, few reasons. The first one is that one can think of developing new light sources. So if we're able to now take this order that happens in the transient domain, and now we drive these systems continuously, we could generate mirrorless lasers that may operate at frequencies for which we cannot build lasers nowadays. Another example for which this may be important is as we push the limit of atomic clocks, what happens is that we're trying to pile up more and more particles to interact with light and to generate this clock. We care about building atomic clocks because this is how to measure time, which is a very fundamental property. But as we pile them on closer and closer, this type of physics may switch on, and this may lead to correlated decay and may limit how well our atomic clocks may perform. On the other hand, it's also true that this type of interactions may give rise to the opposite behavior. Basically, they may make atoms dark, which may basically enhance the time that an atomic clock can operate. Similarly, if we care about building quantum computers or quantum simulators, we're going to start to take into account the fact that as we scale systems up, now there is going to be perhaps unwanted interactions between these atoms. And then on the more provocative side, and just because this is a very broad conference, this problem of photon emission is also related with the problem of photon absorption, which is perhaps, so it may be perhaps interesting in thinking about light harvesting problems such as solar cells or photosynthesis. And another question that comes to my mind is if we can think of this process of emergence of order or coherence arising in biological systems. And with this, I don't mean that quantum mechanics matters for cognition, but what I mean is that perhaps some of the methods that we have developed to deal with these problems that are complex can also be applied to other type of interacting systems. And then last but not least, I just want to say that although I'm a quantum physicist and what I do is kind of separated from humans. I actually think that humans are a very important part in this endeavor. So this is my group of students and postdocs, and I've been at Columbia only 5 years. And I came across very remarkable individuals. I'm very thankful for them. And I should say also that in this slide, I think I counted there are 12 people, but there are 8 nationalities. So really science is a bridge between people, and a very fun one at that. So thank you.